Hi everybody. In this video, we're going to go over some harder projectile problems. This problem will be very similar to uh, type 2 projectiles. So this is going to be more similar with the hang time than anything else. So let's get started. This might be a long video. A world record jump from August 31st, 1986 resulted in Chris Bromham riding a Yamaha motorcycle jumping across a row of cars. Assuming he started and ended at the same level and was airborne for 1.3 seconds, what was the maximum height above the ground for the Daredevil? So let's say he's got this ramp, right? And then we've got car, 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 and then ramp, right? And he's going to jump over like that. It's usually how these stunts work. Now, what we want to do is use the other strategy that I mentioned, where we're going to start halfway, because it wants to know the maximum height, right? And if we just look at what is delta y, and we start at the beginning and the end of the jump, delta y is going to be 0, right? So what we need to do is we need to start at the top and see what it's like to come down from the peak down to the bottom of the jump, right? So that's how we're going to solve this problem. All right, so if we start there, that means that in the y, right, v naught is 0 because it's at peak, right? Acceleration in the y is negative 9.81 meters per second squared. The time is 1.3 seconds. We want to know delta y, and we don't know v final, right? So let's look at our options in the orange equations. We have vf equals v naught plus at. We have vf squared equals v naught squared plus 2a delta y. Then we have delta y equals v naught t plus 1/2 at squared. So what can we eliminate? Well, v naught is 0. So those components go away. We have time. We don't have delta y. We also don't have v final. So this has 2 unknowns, right? This one, that's got 2 unknowns. We don't want to use that. This first orange here, that doesn't even have delta y, so that's no use to us. But here we have delta y is what we're solving for. We have acceleration and time. So let's use that. Delta y equals v naught t, which is 0, plus 1/2 at squared. This would be 1/2 times the negative 9.81 times 1.3. So let's put that into our handy dandy calculator. And we get negative 6.377. Negative 6.377 meters. Now, it's negative. Is that allowed? Well, yes, because we started at the top and we wanted to see how far the motorcyclist fell, right? But that wasn't the question. The question was, what is the maximum height? So the maximum height shouldn't be given as negative. You should rewrite that as 6.377 meters. That would be the maximum height, not negative. So you found the number. Now you need to explain your conclusion by changing that. We also, if we want to look at sig figs, the only measured item we have there is 2 sig figs. So if we want to round this appropriately, that would be approximately 6.4 meters for an appropriate sig fig answer. Okay. All right, let's keep on moving. 413. changing projectile angles. So we've got a couple images here. Number one asks, does the horizontal component of velocity matter for hang time? Okay, so let's look at this over here, right? So we have an object that is launched at a given angle. It peaks up here where the velocity in the y is 0, and then it returns down to the bottom at point B, right? Now, the velocity in the x direction does not accelerate, right? And even on the previous problem with the cannon, when we solved for the x side of the problem, it actually gave us an incorrect answer and we had to use the y side. So whoops, here, let me fix that. If we use v of x, right, it does not matter if we're talking about hang time, right? Because all that matters is that your Vy is measured, because your Vy is going to determine the speed at your launch, how long you're in the air until you hit 0 and then come back down. The faster that velocity, the longer it takes for it to accelerate down to 0 and then to return to Earth. It doesn't actually matter what the x component is of your velocity unless the angle starts getting too low and there's too much in the horizontal component, not enough in the vertical component, then it starts messing with it, but that's not really what the problem's asking, right? All right, number 2, assuming a series of jumps at the same initial speed and various angles, right? So let's look over here. This is what it's talking about, right? We've got the velocity is 50 meters per second, and we have various angles, right? Now, the first question asks, what angle maximizes hang time, right? So this is showing distance. This doesn't show time, but we can intuit what the answer should be, right? So if we have this angle of 15 degrees, that's obviously not going to have very long hang time. What we want to do is we want to get higher and higher and higher until we actually just go straight up and down, right? So the angle that has the greatest hang time, that would be 90 degrees. Okay, that's because there is no horizontal component. The V naught, instead of being split into X and Y, all of the energy goes straight vertical. So that is when, and then the acceleration, right, is having to battle the entire vector V naught instead of breaking it up into X and Y, and only the Y part doing the fighting to keep in the air. So that would be the angle that maximizes hang time. Now, why does a 45-degree angle maximize the range of a projectile? So if 90 degrees maximizes time, why does a 45-degree angle maximize distance? So let's look. If we have a 15-degree angle here, but we also have a 75-degree angle here, they both land at the same spot. So we have 15 and 75 have this shared relationship. Then we also have, we'll use green. Then we also have 30 and 60. So both of those angles have a relationship, 30 and 60. But then 45 has the maximum distance, given that they are all launched at the same speed, right? So what is the similarities here? Well, complementary values right here, complementary values of the initial angle theta result in the same value of r. That basically means if they add up to 90, they will have the exact same distance. So 45 and 45, that adds up to 90, right? those are the only angles that maximize distance. 30 and 60, that equals 90. 15 and 75, that equals 90. If you had 10 and 80, those would also reach the exact same distance. If you had 50 and 40, those would have the exact same distance. Now, one is going to peak higher. One might have a longer hang time or a shorter hang time than the other, but they will go the exact same distance. Right? Now, that is the balance of hang time in the Vy versus distance in the Vx. At 45 degrees, we have, let's see if I can do this. At 45 degrees, the y component is going to be equal to the x component. So the y component really wants a long hang time, right? If you have a y component, it's trying to keep you in the air as long as possible. The x component is really shooting for distance. It wants you to go as far as possible. So when we have 45 degrees, okay, at 45 degrees, y equals x, they're going to be the exact same component. So you have a balance of hang time versus distance. Now, if you have too much of one or not enough of the other, then you're going to lose some distance. You're either going to get more hang time or more distance for your buck, right? But to get that perfect balance and to get the maximum range, you'd need 45 degrees, right? Okay, so that's our discussion on changing projectile angles. Complementary angles that measure to equal 90, will have the exact same range, given the same velocity, right? All right, so car on a cliff. A surfer parks his car on a cliff overlooking the ocean. The cliff is on an incline that makes an angle of 22 degrees below the horizontal. While running to catch a wave, the car begins rolling down the incline with a constant acceleration of 2.5 meters per second squared for 40 meters to the edge of the cliff, which is 35 meters above the ocean. So we're going to need to draw this up. Ignoring air resistance, calculate the position of the car when it lands relative to the base of the cliff and the time it is airborne, right? So let's draw it. Let's see. I will draw right here so I can have that information available. So the incline, right? We've got cliff, incline of 22 degrees above the horizontal. The slope, the incline, is 40 meters. Then the edge of the cliff is 35 meters above the base. Now we want to know how far away from the base of the cliff did it land and the time airborne. So we want to know delta x and time. So what we're going to do is we're going to need to split this up into two parts. First part, right, we have the incline. Second part, we have the projectile. So as it's going down that incline, it's not a projectile yet, it's just a general kinematic problem. So let's work this first part out, okay? We have an acceleration of 2.5 meters per second squared. Instead of calling this delta x, because we've already got an x and a y, let's call this delta r for its displacement. It is displaced 40 meters. The angle theta is 22 degrees. Our v naught is 0 because it starts at rest and the car just begins to roll, right? We do not have time, and we do not have v final. But what we need is v final, right? V final for 1 is going to equal v naught for part 2, right? So that's what we need to find here. So let's look at what we have. V final equals V naught plus AT. Well, we don't have T, so that won't work. Delta R equals V naught T plus 1/2 AT squared. Again, we don't have T. And then V final equals, V final squared equals V naught squared plus 2A delta R. Let's see, we have V naught, we have A, we have delta R. That should be a slam dunk. We'll just plug and chug on that one. So V final is the square root of V naught squared, which is 0. So 0 plus 2 times 2.5 times 40, all under the square root. So let's see, we have 2 times 2.5 is 5. 5 times 40 is 200. Square root of 200, I don't know that one. 14.14. Move you out of my way. 14.14 meters per second. So that is our V final for part 1. That will also be our V naught for part 2 because it's going straight into the next problem. Okay. All right, we're also going to assume 0 at the edge of the cliff. We are not going to assume that the cliff drops off at 22 degrees, right? We're assuming that that 14.14 is purely in the X. So let's mark that off, right? So we have V naught in the X will be the full 14.14 meters per second. Delta Y is 35 meters, but don't forget it's falling, so that is negative. A in the Y is negative 9.81 meters per second squared. A in the X is 0. We want to know delta X, and we want to know T. V naught Y is 0, and we don't know anything about V final. Okay, so let's go ahead and look at what we have equation-wise. So we have V final equals V naught plus AT. We have delta R equals V naught T plus 1/2 AT squared. Then we have V final squared equals V naught squared plus 2A delta R. And I'm using R generically because we have delta X and delta Y in the problem. So let's figure this out. What we'll do is we will first find V final. So we need to do that in the Y because V final in the X is going to be the same since there's no acceleration. So let's find V final. We don't have time though. So let's check on this guy. We have V naught in the Y. We have A in the Y. We have delta Y. So let's use that. We want V final in the Y equals the square root of 0 squared plus 2 times negative 9.81 times negative 35. And right there, the math is going to check you. If you don't have that negative on your delta Y, then you're going to square root a negative number and everything just blows up, right? So let's do that math. We have the square root of 2 times 9.81 times 35. I've got 26.21 to keep that consistent. Okay, so 26.21 is our V final in the Y. Negative 26.21 meters per second. Now remember, every square root, right, has a plus or minus in the front. So you, as the mathematician, as the physics expert on the problem, you get to determine if that's going to be positive or negative. Okay? So here it has to be negative because it is falling downward. Okay? So we've got v final. So what we're looking for is delta x and t. Let's find t using the y part, and then we will plug that in over on the x side. So to find t, let's use this equation, the first one, first orange. We have v final, we have v naught, we have acceleration, and we need time. So let's solve that for time. Time equals v final minus v naught, which is 0, all divided by acceleration. So we have negative 26.21 divided by a negative 9.81. Again, the math is going to check you. If you didn't make your v final negative, you're going to have a negative time, which again does not work. So we have negative 26.21 divided by negative 9.81. Whoops. So that is 2.672. And then we will use that time to find delta x using the second orange, right? We have time, acceleration is 0, so that actually just goes away. So then we have v naught, which is 14.14 times our time. So let's do that. All right, delta x equals v naught t plus 1/2 at squared. Acceleration is 0, so that can all go away. So we have 14.14 times the time, which is 2.672. So we take 2.672 times 14.14. We've got 37.78, which sounds about right because it's 35 meters up. 37.78 meters, that's not an extreme number. That's not something that we really need to start doubting. So that is going to be our answer for that problem. Okay? So that one, you've really got to analyze your orange equations, see what you have, what you don't have. All right, sorry for that. So those are the harder projectile problem that we had. We will continue on in the next video for uniform circular motion.